On August 23, 2023, India made history. With a successful landing of Chandrayaan-3, India became just the fourth country ever to touch down on the moon and the very first to reach its elusive South Pole. In just a few short weeks, the mission's lander Vikram and its rover Pragyan explored an untouched, mysterious region no nation had dared visit before. And what they found sparked global curiosity. But the most jaw-dropping moment didn't happen right away. 3 days after landing, something extraordinary happened. A seismic instrument on board, the Instrument for Lunar Seismic Activity, or ILSA, picked up what could be a moonquake. That's right, the moon shook. Moonquakes are just what they sound like, tremors or seismic rumbles on the moon's surface. The last time we had solid evidence of such activity was way back in the 1970s during the Apollo missions. So if ILSA's data holds up, this would be the first confirmed moonquake in over 50 years. But why does that matter? Well, to scientists, it's a big deal. These tremors could reveal what's going on deep beneath the moon's crust, its internal structure, tectonic activity, and maybe even clues about how the moon evolved over billions of years. That kind of information is priceless for anyone planning to build lunar habitats or long-term research stations, because if the ground's gonna shake, we need to know when, where, and why. Chandrayaan-3 didn't stop there, though. The mission's South Pole gathered groundbreaking data. The rover analyzed the soil, mapped surface temperatures, and confirmed the presence of certain elements. It was a gold mine for lunar science. But there's one thing, a big thing, it didn't find. Just like the missions that came before it, Chandrayaan-3 failed to detect liquid water on the moon's surface. While ice has been suspected and detected in permanently shadowed craters, scientists were hoping for more conclusive proof or even signs of usable water. So far, that puzzle piece is still missing. So what does all this mean? India's moonshot is more than just a win for science. It's a bold statement that space exploration isn't just the playground of a few rich nations. But as exciting as the mission's findings are, they've also sparked even bigger questions. Is there water that can sustain future astronauts? What exactly causes a moonquake? And what else is hiding in those shadowy lunar craters? Stick around, because this story is just getting started.
To really understand why India's Chandrayaan-3 mission was such a big deal, you've got to know exactly where it touched down on the moon and why that location changes everything. Let's start with the basics. The moon has two sides, a near side and a far side. The near side is the part we always see from Earth, the familiar face of the moon that lights up our night sky. Every manned lunar mission to date, including the famous Apollo landings, has taken place on this near side. The far side, on the other hand, is a mystery to us here on Earth. We never see it because the moon is tidally locked, meaning it spins on its axis at the same speed it orbits Earth, roughly every 27.3 days. So one side always faces us and the other stays hidden. Only one mission in history has ever made a soft landing on that far side, China's Chang'e 4. Now, here's where it gets exciting. Chandrayaan-3 didn't land just anywhere. It's set down near the moon's South Pole, one of the most extreme, least explored places in the solar system. Its landing spot, now proudly named Shiv Shakti Point, sits about 600 kilometers from the actual South Pole, at coordinates 69.3 degrees south and 32.3 degrees east. Technically, it's still on the near side of the moon, so yes, it's visible from Earth. But this location pushes right up against the edge of what we've been able to explore, and that comes with some serious challenges. Challenge number 1, the terrain. The lunar South Pole is nothing like the flat plains the Apollo astronauts strolled across. This region is rugged, jagged, and wild. It's filled with deep craters, sharp cliffs, and steep slopes. Some areas are in almost constant shadow, others catch light at weird angles. That kind of landscape makes it incredibly hard to find a safe place to land, and even harder to guide a spacecraft down without crashing. Challenge number 2, the darkness. Near the South Pole, sunlight barely skims the surface. Some craters are permanently shrouded in darkness. They haven't seen sunlight in billions of years. That's a nightmare for solar-powered landers and rovers, and it also means extreme cold. We're talking temperatures that can plunge to minus 400 degrees Fahrenheit. Operating in that kind of environment is a test of engineering on another level. And there's a third major challenge, which we can explore next: communications and data relay, since those shadowy areas make it harder to maintain line-of-sight contact with Earth. But despite all these challenges, Chandrayaan-3 made it. And that's why this landing wasn't just a technical milestone, it was a statement. India didn't just land on the moon, it reached for the most dangerous, least understood part of it, and stuck the landing.
One of the biggest reasons the moon's south pole is such a tough nut to crack comes down to something simple but brutal: light, or the lack of it. Because of the moon's slight tilt on its axis and the extreme depth of the craters near its south pole, sunlight barely reaches this region. The sun just kind of skims the horizon during the lunar day, never rising high above the landscape. That means solar panels don't get enough energy, which makes powering landers and rovers incredibly challenging. And it gets even more intense. Some craters near the South Pole are so deep and shadowed that they haven't seen sunlight in over 1 billion years. That's right, billion, with a B. These are places locked in eternal darkness, where sunlight simply never touches the surface. Now mix in the cold. During the lunar night, which lasts about 14 Earth days, temperatures can plummet to a staggering -382 degrees Fahrenheit, -230 degrees Celsius. That kind of cold doesn't just slow things down, it threatens to freeze and destroy electronic components, batteries, and delicate instruments. It's like sending a robot into a deep freeze and asking it to survive long enough to send back valuable data. So how did Chandrayaan-3 handle it? The mission was designed to operate for 14 Earth days, essentially the length of a single lunar daytime. That's when there's just enough sunlight to keep the systems running, collect data, and move the rover. And in those 2 weeks, India made history. Again, let's talk discoveries. Chandrayaan-3 kicked things off by taking a closer look at something most people don't even realize the moon has: an atmosphere. Well, sort of. The moon's atmosphere is ultra-thin, technically called an exosphere. It's so thin, it's basically a vacuum. For comparison, the pressure in the lunar exosphere is around 0.3 nanopascals. That's about 1/1,000,000th the pressure of Earth's atmosphere at sea level. In other words, it's ghostly thin. But there's more. Floating at the edge of that exosphere is a secondary layer called the ionosphere, formed when sunlight energizes atoms and particles in the exosphere, turning them into a weak plasma field. Until now, very little had been measured about this region. That changed with Chandrayaan-3. Using instruments aboard the Vikram lander, Indian scientists were able to make the first ever temperature and density readings of this plasma layer near the moon's south pole. What they found? A thin, roughly 100-kilometer thick layer of electrically charged particles hovering near the surface. It's relatively sparse, but it exists, and that changes how we think about the moon's environment and its interaction with solar radiation. This discovery is a big deal because understanding the moon's plasma environment is key to future missions, especially those involving communications, long-term landers, or even lunar bases. And this is just the beginning. Want me to continue with the next section? We can go deeper into Chandrayaan-3's other discoveries, including that potential moonquake, and what it all means for the future of space exploration.
So here's something wild. The moon's surface might look empty and silent, but just above it, there's an invisible layer of energy that could shape the future of space travel. We're talking about the lunar ionosphere, a super thin layer of plasma floating above the moon's surface, packed with between 5 million to 30 million electrons per cubic meter. Sounds like a big number, right? But in space terms, that's actually really sparse. And here's where it gets interesting. The density of that plasma changes throughout the lunar day as sunlight hits different parts of the surface and charges particles in the atmosphere. Why does that matter? Well, it turns out that electron density in the ionosphere affects how radio signals travel. The more dense the plasma, the more it slows down radio waves, kind of like swimming through honey instead of water. But because the moon's ionosphere is so thin, any delay in radio signals would be minimal. That's a huge relief when you're thinking about future lunar navigation, robotic operations, or even human communication systems. Basically, it's one less thing we'll have to worry about when we eventually set up shop on the moon. But wait, it gets even cooler. Literally. The The Vikram lander wasn't just looking up into space. It also dug down into the moon's surface to get a read on what's happening underground. It deployed a temperature probe with 10 sensors, designed to burrow about 10 centimeters, roughly 4 inches below the surface. What it found was shocking. Literally, a 70 degrees Celsius or 126 degrees Fahrenheit temperature drop in just a few inches. Here's how it breaks down. Right at the surface, where the sun's rays hit during the lunar day, the temperature can hit 140 degrees Fahrenheit or 60 degrees Celsius. But just 3 inches or 8 centimeters below, the temperature drops to 14 degrees Fahrenheit or negative 10 degrees Celsius. That's a crazy fast drop. And what does that tell us? It shows that the moon's topsoil, called regolith, is an incredible thermal insulator. That dusty gray surface may not look like much, but it holds in heat like a high-end thermos bottle. And that's a big deal if we ever plan to build shelters or habitats on the moon. Why? Because the moon doesn't have an atmosphere to protect people from wild temperature swings or dangerous radiation. But if lunar soil can insulate against extreme heat and cold, we might be able to use it to build protective structures like bunkers, bases, or even 3D printed habitats. Think of it this way: the very ground astronauts walk on could one day be the material that saves their lives. So between what we're learning above the surface and beneath it, Chandrayaan-3 is not just exploring the moon, it's helping to map out how humans might actually live there one day.
Just 3 days after Chandrayaan-3's historic touchdown on the moon, on August 26th, something remarkable happened. One of the mission's key instruments, the Instrument for Lunar Seismic Activity, ILSA, picked up a strange tremor. It could be what scientists call a moonquake, a seismic shakeup happening not on Earth, but on the moon. Now, moonquakes aren't exactly new. We've known about them since the Apollo missions in the 1970s. But what makes this event so exciting is how rare it is and how little we still understand about it. So, what causes these moonquakes? There are 3 main suspects: meteorite impacts. Picture space rocks slamming into the moon's surface at insane speeds. These collisions send seismic waves rippling through the crust, similar to how throwing a stone into a pond creates ripples. Tidal forces. Just like the moon affects our tides, Earth's gravitational pull can tug at the moon too. Combine that with the sun's gravitational influence, and you've got a cocktail of stress and strain that can make the moon flex and bend, causing it to quake. But here's where things get wild. Moonquakes don't behave like earthquakes. On Earth, a quake might last a few seconds to a couple of minutes. On the moon, these quakes can linger for up to an hour, and they often occur in clusters, like aftershocks that won't quit. That's unusual, and it raises a big, fascinating question. What's really going on inside the moon? In recent years, scientists have floated 2 bold theories. Theory 1, the moon is shrinking. Yes, shrinking. As the moon gradually cools over time, its interior contracts, but the outer crust doesn't go quietly. It cracks under the pressure. That cracking creates faults in the lunar surface, just like what we see during earthquakes on Earth. And every time one of those faults shifts, it could trigger a moonquake. Theory 2, the moon is heating up. Sound like a contradiction? Maybe not. There's a possibility that deep inside the moon, radioactive elements are decaying, releasing heat from the core outward. That heat could be melting parts of the moon's interior, forming pockets of magma. If that's happening, it's a huge deal, because molten rock moving beneath the surface could create pressure buildups that eventually lead to moonquakes. Either way, the message is clear. The moon isn't just a dusty, silent rock drifting in space. It's alive, geologically speaking, and Chandrayaan-3 may have just cracked open a new chapter in understanding its hidden heartbeat. Scientists are still digging into the mystery behind the seismic activity picked up by Chandrayaan-3. What exactly triggered that moonquake? Nobody knows yet.
But one thing is clear, this is the first seismic event detected on the moon in over 50 years. That alone makes it a major scientific milestone. And why does it matter? Because these kinds of tremors could offer us rare clues about the moon's interior structure and origin story, what it's made of, how it formed, and whether it's still geologically active deep beneath the surface. But that wasn't the only breakthrough from India's lunar mission. The next big reveal came from the Pragyan rover, equipped with a powerful instrument called the Laser-Induced Breakdown Spectrometer, or LIBS for short. So what exactly does LIBS do? Think of it like a high-tech elemental detective. It fires short, intense laser pulses at the moon's surface. These laser shots vaporize the material into plasma, a super-hot, glowing state of matter. LIBS then analyzes the light coming from that plasma to identify what elements are present based on their unique spectral signatures. The results? Pretty incredible. The rover detected a whole host of elements: aluminum, calcium, chromium, iron, manganese, oxygen, titanium, and silicon, all expected. But then came the surprise: sulfur. And this is where things get really interesting. Why is sulfur a big deal? One leading theory about the presence of water on the moon centers around something called cold trapping. Here's how it works. In the eternally shadowed, freezing cold craters near the lunar South Pole, water vapor drifting across the surface can get trapped as solid ice. Temperatures in these regions are so low, they've been described as colder than Pluto. In these icy traps, sulfur and other molecules could also become frozen, alongside water. Now, when high-energy solar radiation hits these ice deposits, it can break apart the molecules, releasing sulfur in the process. So the presence of sulfur might mean there was, or still is, water ice in those shadowed regions. But sulfur tells another story too. It's a key marker of volcanic activity. If sulfur is buried in the lunar soil, it suggests the moon may have experienced intense volcanic eruptions in its past. That gives scientists valuable clues about the moon's ancient geological history, how it evolved over billions of years. Here's the twist. No lunar orbiter, not a single one, has ever detected sulfur near the moon's south pole. So for the Pragyan rover to find it there, right on the surface, is a discovery that could rewrite part of our understanding of lunar science. But even with all these major wins, there's one thing the Chandrayaan-3 mission didn't find. And it's something scientists and space agencies have been hoping to confirm for years: water ice. Despite its close proximity to shadowed craters and all the right environmental conditions for ice to exist, Chandrayaan-3 was unable to detect any, not on the surface at least. And that leaves a huge lingering question. Is the moon hiding water ice deeper below, or is it simply not there?
Back in 2008, India's Chandrayaan-1 mission made a groundbreaking discovery with its Moon Mineralogy Mapper, better known as the M3 instrument. It detected signs of hydroxyl molecules, basically water-bearing compounds, in the moon's polar regions. This was the first solid hint that water, or at least water-related molecules, might be hiding in those frozen lunar corners. But here's the thing. That data didn't get fully unpacked overnight. Scientists spent over a decade analyzing those readings, digging deeper and deeper into what they really meant. Then, in 2018, a dedicated team finally confirmed something huge. Using that M3 data, they identified 3 distinct signatures that definitively prove water ice exists right there on the lunar surface. Fast forward to Chandrayaan-3 mission, and things get puzzling. Despite all the past evidence, the Pragyan rover, like so many missions before it, has yet to find direct proof of water ice where it's been exploring. This brings us to a big question. If Chandrayaan-1 showed water ice was definitely there, why hasn't Pragyan found any? And what does the sulfur discovery mean in all this? There are 2 likely answers. First, Pragyan might have just been in the wrong spot at the wrong time. That 2018 study also revealed that water ice on the moon isn't spread out evenly. Instead, it's patchy and scattered, kind of like finding pockets of snow in some shaded craters, while other areas remain dry. At the moon's south pole, for example, most of the water ice tends to cluster inside deep craters, places that never see sunlight.
Meanwhile, the North Pole has water ice too, but it's thinner and more widely dispersed across the surface. So it's entirely possible that the Vikram lander and Pragyan rover touched down in an area where water ice simply isn't present, at least not on the surface. This patchy distribution means finding water ice isn't as straightforward as first thought. It's a bit like searching for hidden pockets of treasure scattered across a vast and rugged landscape. Sometimes you find it, sometimes you don't. And that mystery only makes the search for lunar water even more compelling and important for future missions and potential human settlements on the moon.
The second explanation actually comes from one of Chandrayaan-3's own discoveries. The CHAOS-TE instrument on the Vikram lander recorded a dramatic temperature drop just beneath the lunar surface, about 70 degrees Celsius. That's a staggering 126 degrees Fahrenheit, cooler only 8 centimeters down. This sharp dip tells us something important. The moon's soil is a terrible conductor of heat. What does that mean for the search for water ice? Simply put, the water isn't likely sitting out in the open on the surface. Instead, it's probably hiding beneath the ground, insulated by that thick layer of lunar dust and soil. So the real prize lies underground, where temperatures stay low enough to preserve ice. Now, Chandrayaan-3's mission was designed to last just 2 weeks, one lunar day, because the harsh cold of the lunar night makes survival nearly impossible for the lander and rover. After that, any contact would have been a surprise. India's space agency tried to re-establish communication once the lunar night ended and sunlight returned, but Vikram and Pragyan didn't respond. Still, the mission was a huge success. It achieved its primary goal, a soft, precise landing on the moon's challenging South Pole, and collected an incredible amount of valuable data along the way. The South Pole is the moon's most promising region for resources, and Chandrayaan-3 has opened a treasure chest of new insights about it. Building on this momentum, India is now teaming up with Japan for Chandrayaan-4, a mission that will send another lander and rover to the lunar South Pole. This time, the goal is even bolder: to make a direct, on-the-ground discovery of that elusive water ice buried beneath the moon's surface. The search continues, and with every mission, we get closer to unlocking the moon's secrets.